Okay, this is the last hour of Physics 1C for September 24th, and we're going to be talking about the way in which voltage is connected to um, current, and that forces us to talk about something that's called resistivity. All right. So let's get started talking about resistivity. Resistivity is a property of materials, and this little chart is going to kind of describe what it is. So resistivity, it's related to the way in which certain materials will slow the flow of current within a system. And this chart, just a bunch of numbers combined with this equation down here, effectively tells us what we need to know about resistivity. Okay? So different materials resist the flow of current in different ways. And there's different types of materials. There are conductors, there's semiconductors, there's insulators. Conductors are effectively metals, silver, copper, gold, aluminum, etc., and alloys of those metals. The resistivity values are given in this unit: ohms times meters. What is an ohm? It's effectively a unit of resistance, and we'll get there. It's also related to a ratio of voltage over current, but just we can look at these numbers and get some kind of a feel for what it represents. These numbers are something times 10 to the negative 8. Okay, they're all within that range right there. Semiconductors, kind of a different story. We're not going to talk much about semiconductors in this class, but the biggest thing I want to notice here is the difference between the insulators versus the conductors. All of the conductors have resistivities that are on the order of 10 to the negative 8. All of the insulators have resistivities on the order of 10 to the 14. The insulators are things like amber, glass, lucite. Other things not listed on here would be like rubber, plastic, all these types of things. The resistivity of these things is massive. That means that it is very difficult to make electricity flow through wood. I don't think that comes as too much of a surprise to you. That it's difficult to get electricity to flow through glass. It's difficult to get electricity to flow through mica, which would be like rock or quartz or sulfur or Teflon or anything like that. Okay. It's easy to get electricity to flow through all of these things over here, and that is effectively what resistivity is. Mathematically, this is what resistivity is. The resistivity of a material is related to the ratio of the size of the electric field that's produced to the magnitude of the current density that's caused by that electric field. Okay? So if the resistivity is low, then, that means that you get a big current density for a given electric field, right? Now, I find this equation to be very hard to understand when I look at it. Okay, it does tell you that there's a kind of a fixed ratio between the electric field and the current density. I will also say that the name of this expression is called Ohm's law, but there is definitely an easier way to understand it. And the easier way to understand this relationship right here is by doing the following. The current density J is defined as current divided by area. The electric field that might be set up, let's say, for example, in a wire. So suppose that I have a wire. Let's say it's made of copper. Okay. And let's say that we know that the electric field in this wire, E, points this way. If the electric field goes that way, that means that also our current density, the flow of the charges within the system, also flows in the same direction. These are both vectors. And let's say that we also know something about the length of our wire. Let's say the length is L. Let's say the cross-sectional area over here is A. And I think that's all I need to say about it. Then we also know something about the potential difference between the two ends of the wire here and here. What would the potential difference between the ends of the wire be? If the electric field is E, I tell you it's a uniform electric field, and I tell you the length of the wire is L. What would the potential difference between one side of the wire and the other side of the wire be in that case? Assuming the electric field is constant within here. E times L, exactly. Okay, let's put this equation, Ohm's law, together with these two expressions here. Let's eliminate E and let's eliminate J, okay? Now our equation for Ohm's law is going to say the following. It's going to say that rho is equal to, so E is just delta V divided by L. J, current density, is I divided by A. Okay. And now let's rearrange this. I multiply the L to the left-hand side. The area is the denominator right here, so once I move it over to here, it's still going to be down here. If you work out the math, it's definitely going to kind of flip up here. You'll divide it to the other side. We get this expression. Now, this quantity on the left-hand side is referred to as resistance. This is the quantity that is much more commonly found when we're describing electrical systems, is resistance. And we use the letter capital R for resistance. It's defined as resistivity of the material multiplied by the length of the material divided by the cross-sectional area of the material that we're using. And commonly what we're going to be describing here are wires, right? So the area will be the cross-sectional area of the wire, L will be the length of the wire, and this is a quantity that we call resistance, okay? Now, with this definition, comparing back to this equation right here, the other way that we can describe resistance is that it's related to the potential difference between the ends of the wire divided by the current in the wire, okay? Or the more common way in which this equation is written, and this is often what's referred to as Ohm's law, so when I say Ohm's law in this class, this is usually what I'm going to mean, is the potential difference delta V is equal to I multiplied by R. That's like the most common version of Ohm's law that you're going to see. When people use the expression Ohm's law, this is what they're referring to, is that the potential difference between 2 points in a wire is equal to the current that flows through the wire multiplied by the resistance. And what is the resistance? The resistance is a property of the material as well as a property of how the material is constructed, right? So for a given wire, you're going to have some value for these things. Just to give an example, so if my wire had a length that, let's say, was equal to 10 centimeters, and it's had a cross-sectional area, let's use the area from the previous problem, which was like 3.31, was it, times 10 to the negative 2? Negative 6. And since the negative 6 meters squared. And then we need one other piece, right? We need the resistivity, which is, for copper, the resistivity is given right here, 1.72 times 10 to the negative 8. Ohms times meters. We can use these three quantities to figure out how much resistance our wire has. And when I say resistance, I mean effectively the resistance that it has to the flow of electricity for a given potential difference, right? So this would be equal to rho L over A, or 1.72 times 10 to the negative 8 ohm meters. Ohms is going to be the unit of resistance. Multiplied by length, so 10 centimeters becomes 0.1 meters, and then divided by the cross-sectional area. Now let's look at the number and let's talk about the formula itself and see if it makes any sense. So this gives us so I got 5.19 times 10 to the negative 4. This ends up being about 5.2 times 10 to the minus 4, and the unit is ohms. This would be the resistance of a copper wire that had a length of 10 centimeters and a cross-sectional area of this. This is the value of the resistance. Now, what does that resistance actually represent? I think if we rearrange this equation in the following way, it might make some sense. So say I give you a battery, right? And I connect this battery with a wire that has very small amounts of resistance up to this resistor that we just described here, which is just going to be a fat piece of copper wire. Well, not that fat, I guess, but that happens to have these properties. And I tell you the resistance of this object is 5.2 times 10 to the minus 4 ohms. Okay? and then I tell you that the battery that I have connected down here has a potential difference across its nodes of 9 volts. Okay, so that's my system. I've got a battery. It's connected to a piece of wire that has a resistance of 5.2 times 10 to the negative 4 ohms, and I want to know something about the current flowing in the wire. According to this equation, the current that flows through our wire is related to the size of the potential difference in the battery divided by the resistance of our system. Now, I'm leaving out a lot of details here. This wire itself could have some resistance. The battery itself might have some internal resistance. We'll get into all that stuff later. But for now, I would say the current flowing in my system is going to be equal to the potential difference delta V, which is 9 volts, and then we would divide by this, a very, very tiny amount of resistance, by the way, and this is going to produce a very sizable current, a really large amount of current. How much? It's going to be, that's a 4, not a 9. I can't really help it from doing that. It just automatically connects those things. So you take 9, you divide by the answer we got a second ago, and this is a huge amount of current. This is a totally ridiculous amount of current. 17,320 amps. That is a massive amount of current. It would, if you were able to get that amount of current to pass through your body, which would be very difficult to do, but if you were able to do it, it would 100% kill you. That is a massive amount of current. Your book describes the lab manual goes into detail about how much electrical current the human body can sustain on the first few pages. You can kind of read through that if you want to. Our bodies have a lot of electrical resistance because we're composed of water, not metal. So, yeah. But I would tell you in this system that if I was to connect a 9-volt battery up to a 10-centimeter length of wire that was this long, and that was the only thing that I connected, 100% this whole system would just start to burn. It would just start to burn. Because when you try to pass electricity kind of too quickly through a system, what happens is the electrical charges start to interact with the material so quickly that it just heats up, just like friction. Okay? Heats up through kind of internal friction, and the whole system would probably burn, and the electricity would stop flowing. In your home, there's a circuit breaker that prevents stuff like this from happening, okay? But I really want you to just think about this equation now, and like what it says. And I want to think about this equation too. I want to think about these two equations. So the equation says that the current that's produced is equal to the electric potential difference that's produced. This is basically your source, right? You've got some battery, or you've got a wall socket or something like that, and then you have to divide by the resistance, right? Does this make sense? Delta V is a type of energy per unit coulomb, right? And I, current, is the rate of flow of charges, right? And what this tells us is that if I take the potential difference, the energy that I have to work with, and I divide by the resistance that I have to the flow of electricity, that's going to give me the current that flows in the system. If there's a lot of resistance to flow, like if R is big, the current will be very small. What would R being big be? Well, I will say inside of like a voltmeter, for example, inside of a voltmeter, like the ones that we use at school and some that you could just buy at any kind of electronics store, have a resistance of about 10 times 10 to the 6th ohms. Okay? If I was to connect a 9-volt battery up to a voltmeter, the current that would pass through the voltmeter would be very, very small. It would be on the order of 10 to the negative 6. If I used delta V equal to 9 volts for this, then the current would flow on the order of, what would it be? It'd be like 10 to the negative 6 amps, right? Microamps. Very small amount of current would actually flow through the voltmeter. Okay, does this relationship make sense to you? That the current that you get is related to this, the voltage, the energy you have, divided by the resistance. The more resistance you have, the less current flow you're going to have, right? So think about something like this, like these things like mica, which is rock. Imagine that you're trying to pass electricity through rock, okay? The resistivity of mica is gigantic. So if you try to pass electric current through rock by, for example, taking a battery and attaching it to the rock, like no electricity is going to flow through it. That's what this says. Like very, very small amounts of current would actually flow. There'd be no electrical flow of current, right? However, when you connect it up to a metal, you get a lot of electric current flow. That's what Ohm's law tells us. So let's think about what resistance is then. So resistivity is something you're just going to have to kind of accept that it's a property of different materials. It's a measurable property. It's something we can physically measure. We can measure resistivity, so it's an empirical property of materials. Different materials have different resistivities. That's just the way that it is. But resistance itself, we can kind of come to understanding of why it works the way that it does. Now, this tells us that the longer the wire is, the more resistance to electrical flow you're going to have is. Does that make sense to you guys? Does it make sense that the longer the wire is, there's basically just, there's more material, right? There's more material, therefore there's a lot more stuff for the electrons to interact with, therefore more length to get through as well, exactly. What about the part on the bottom? This tells us that the bigger, not smaller, the bigger the area of the wire, the smaller the resistance to electrical flow is going to be. Does that make sense? Yes, like the wider the street, the more cars can pass through. Exactly, Nathan. That's exactly right. Okay, so hopefully this idea of what resistance is makes some sense to you. And again, remember, the resistivity is just going to be a property of materials themselves, and it's just the way it is. But yeah, this is kind of one of the fundamental equations we use a lot in this class. You know, some people might say it's kind of similar to F equal to ma for electricity. I'd say it's more similar to force is equal to B times V, the drag force. This is kind of like drag force equation. It's kind of similar to that because you've got a flow of charges multiplied by a resistance, and they're driven by this potential difference here. All right. So we've defined what these quantities are. We've now connected this idea of electric potential to electric current. So electric potential is what we've been discussing for 2 chapters now. The idea of resistance connects these two to each other through this equation called Ohm's law, which is, we're going to be using it quite a bit over the next chapter or two, and really throughout the course. Okay, so the next thing, does anyone have any questions before I keep going? All right. By the way, you mentioned electrocution, so I'm just going to point out that it's not about voltage in terms of what's going to harm you. It's about current. Okay? Just having a lot of voltage isn't enough to electrocute someone or to cause physical damage to them. You need to have a large amount of current pass through your body to suffer any type of physical problems. What could those be? Those could be a tightening of your muscles up to cardiac arrest. But I will say that your body has a very high resistance to the flow of electricity. But when your body is wet, the resistance to flow of electricity is very small. So it's much more easy to get electrocuted when your body is wet versus when your body is dry. When your body is dry, it's a lot harder. When your body is wet, it's a lot easier. Okay. All right. Any questions before we move on to the next topic? Isn't water an insulator? Well, I think it's more that, like, our body, when wet, like, taking into account all the things that our body is made of, and water can have different properties. I don't know if I would say, is water an insulator? Water with, like, salts inside of it can allow electricity to flow, I believe. All right, so the next thing to talk about is this. I guess we could do this problem too. Maybe we do this problem first. Let's do this problem real quick. So we'll talk about resistance and temperature here in a second. Let's pretty quickly do this problem right here. Okay, this is a very plug and chug problem. We'll go through this relatively quickly so we can get to some more topics here. 18 gauge copper wire has a cross-sectional area of 8.2 times 10 to the negative 7 meters squared. It carries a current, so current's I, of 1.67 amps. We want to find the electric field magnitude in the wire. We're going to need some other pieces of information. Are we? Let's see. Oh, no. We won't. We're good, I think. We have copper, so we'll have to write down. We're going to need the resistivity. Resistivity of copper is 1.72 times 10 to the negative 8. The first question is to find the electric field in the wire. I believe for this, we're just going to use this relationship right here that says that the electric field is equal to J times rho. So this is going to be equal to the current density multiplied by the resistivity. The current density in this case is going to be equal to, J is just I over A. So this is going to be I divided by the area of the wire multiplied by the resistivity rho. So we're going to get that the electric field is going to be equal to, just plug all these numbers in here, 1.67 amps divided by 8.27. And then we need to multiply by rho, which is this right here. So that gives us electric field. What's that equal to? So maybe I already calculated it. Oh, wait. I got something different. I got 3.5 times 10 to the negative, like 0.0347. This would be volts per meter. Okay, you guys agree? Part B, potential difference between 2 points in the wire that are 50 meters apart. How do I do that? This should be pretty easy. Delta V is equal to E times L. So we just take 0.0347 volts per meter, multiply by the length. You're saying it's 1.75 volts. 0.035 times 50, so you're going to move this over 1, multiply by 5 times 35. Yep. It's not 1.85? You're probably right. Yeah, you're right. I got 1.74, but whatever. Something like that. Close enough. And then the resistance of a 50-meter length of this wire. Okay, so part C, if I want to find resistance, we have to do resistance is equal to rho times the length divided by the area. So in this case, that's resistivity. Multiply by length. Where's length? 50 meters. And then divide by area. Units work out when we do this. 8.2 times 10 to the minus 7 meters squared. So about 1.05 ohms is what I got. Yep, it looks like you guys got the same thing. Okay. Pretty easy stuff, right? It's. I will say one thing. Anyone questions at all? I will say, in terms of this equation right here, I know that you've got a homework problem on the lab manual, on the next lab manual homework. And the problem that you have, it looks something like this. You've got like a conical conductor. I think this is what it is. I can pull the problem up, I guess. You've got this conical conductor that has, like, I shouldn't use big R for this now. Radius 1 over here, and, like, radius 2 over here. And then it's, like, I don't know, it's copper or something like this. And you're supposed to figure out what the resistance of this object is. And I'm just going to give you a hint about how you want to solve these kind of problems. I think it probably gives you a similar hint in the problem, but this is our definition of what resistance is. It's rho L over A. I believe what you end up doing in this problem is you kind of create a coordinate system where you cut the objects into little pieces of length dx. And then you say that the resistance of one little tiny piece is going to be equal to the resistivity divided by the area times dx. And you have to integrate. It's not much harder than things that you've done before. I think one thing that's tricky is that the distance that you travel in this direction is going to be related to the area here, because you're going to have some radius at this point, and the size of that radius is going to be related to the slope of this line. Anyway, so just something for you to think about that you're going to have in the future, that these problems can get a little bit harder, but you should be able to figure it out. It's not that tricky. Just have to do some math. Anyway, most of your homework problems, though, not going to be this hard. Most of your homework problems are going to be kind of like this. Very straightforward, like what I'd call plug-and-chug engineering type problems. All right, resistance and temperature. So, I guess I could just ask you... Oh, I want to say something before we move on. Ohm's law, by the way, Ohm's law, this really only works for certain types of systems. When you're talking about semiconductors, this doesn't work anymore. It only works for what are called ohmic conductors. All right? Now, in Physics 1C, this is going to work for every type of conductor that we talk about, okay? But it is an empirical relationship. It is not it is not true for all systems, okay? These are not related to simply for all systems. However, for a lot of systems that matter in terms of this class, I guess, and then probably in terms of when you're studying electrical engineering classes and stuff like that, this is going to be good enough for what you need. In systems in which it's not good enough, you're going to know something about that system and you'll have a different relationship or something like that. Okay? All right, so resistance and temperature. So there's a very straightforward relationship between resistance and temperature. For conductors, as the temperature of the conductor increases, the resistance goes up as well. Okay, so for conductors, the resistance is basically proportional to the temperature. The bigger the temperature, the bigger the resistance is going to be. You can even plot it over some range that as the temperature increases, the resistance also increases. Okay, over some range of temperatures, not over a massive range of temperatures, but over some range of temperatures. Okay, and we can put that into a simple kind of form like this over here. Grab this, and this is the problem we're going to do. So the relationship ends up looking like this. We're going to do this problem later. So resistivity as a function of temperature is given by the resistivity at some reference temperature T0 multiplied by 1 plus alpha times T minus T0. If this equation confuses you in some way, it comes from the definition of slope. If I take rho minus rho naught divided by T minus T0, this is equal to a fixed constant that we call alpha. Okay? Do some rearranging mathematically and you will get that equation up there. So what is alpha? I can't remember if I actually got the chart for this. Alpha is once again, I don't think I grabbed it. Alpha is once again just going to be some number that you look up in a table. Alpha is what's referred to as like the temperature coefficient. And here's a question for those of you that are either taking 1B now or have taken it in the past, we're talking about linear expansion. You know, when we're talking about like when you heat up an object that it expands, we also use this symbol alpha. It's also a temperature coefficient. It has exactly the same units. It's something per degree Celsius basically, yeah. So you can compare these temperature coefficients that show up with this. In fact, let me grab it real quick. Let me just show you what these things are. They're just these numbers. Coulomb's law. We're in the wrong chapter. Not this chapter. This chapter. Resistance. Oh, it's right there. But where are the... I've lost my mind. I know it's at the very bottom of one of these pages. There it is down there. So here's an example of what these values are. They're just numbers. Aluminum is like this. Brass is like this. Carbon has a negative value. And this is because carbon is a semiconductor. And for semiconductors, the resistivity actually decreases with temperature. Also, with semiconductors, the resistivity is related to the ability to add impurities to the substance through a method called doping, where you add small amounts of impurities to the substance and it radically alters the electrical properties of it. Yeah, very simple relationship right here. The same relationship for resistivity also exists for resistance. Resistivity and resistance are obviously related to each other. So resistance as a function of temperature can also be written as resistance at some fixed value multiplied by 1 plus this alpha times T minus T naught. Okay. We're gonna do a problem with this right here. Yeah, it's called doping. That's what they call it. You said you wanted to know about the physics that Intel uses. They work with semiconductors, right? Printed on those boards, they use semiconductors to control processes at the molecular level and to produce these really powerful computers. And the way in which a semiconductor is controlled is by adding little tiny impurities within it that take something like silicon and make it a really powerful object called a transistor that we use to kind of govern a lot of the processes inside of a computer. So conductors act like this. I showed you that semiconductors act opposite to this, that as they heat up, what happens with semiconductors is that as they heat up, the portions of it, like you basically free up more charge carriers in the semiconductor, and that allows them to change their electrical properties and get less resistance as you heat up the temperature, right? So you saw the picture, but I can kind of redraw it right here, so it's in the notes. For semiconductors, it's not exactly an inverse relationship, but it's it's something like kind of like this, that resistance and temperature kind of like as it heats up, the temperature falls because the number of charge carriers goes up. Number of charges that are free goes up. There's a third class of materials that we are only recently kind of learning. I say recently, since maybe the 1960s or so. These materials are called superconductors, and superconductors are really interesting. They have the property that at a certain temperature, and this would be temperature plotted on like the Kelvin scale, and let's say we're talking about, so again, we're talking about resistance here. Let's say we're talking about mercury. Mercury is a type of substance that you guys kind of know it is. This is liquid metal type substance. Mercury over a long range kind of behaves like an ohmic object. Its resistance kind of increases with temperature. But for some reason, at a temperature of something like, I think it's like 4 point something Kelvin. Let's just say 4 Kelvin. I don't want to, whatever. It's 4.3, 4.2, doesn't matter. At an extremely cold temperature of 4 Kelvin, extremely close to absolute zero, for some reason, the curve for mercury completely has this disjoint and the resistance actually drops to zero. Like, I don't mean close to zero. I mean that as long as mercury is below about 4 Kelvin, that within this regime right here, its resistance is equal to 0. So a superconductor is any type of a material that that below a certain threshold temperature, that is often referred to as the critical temperature, labeled as T sub C for critical temperature, that you have kind of a phase change that occurs where the charge carriers start to group together and little pairs of electrons start to move together in these things that are called group pairs. And if you want to study superconductors, this is a branch of science right now that is extremely kind of important in terms of pushing science forward. If like 4 Kelvin is really cold, right? Superconductors have a lot of really interesting properties. For example, you could imagine that if we could transfer our power along superconducting lines, there would no longer be any loss of heat to the resistance of the wires. As I mentioned before, whenever you try to pass electricity through a wire, for example, if you tried to pass this much current through a copper wire like we described, it would cause it to burn up. So when we're transferring electricity between our cities, there's an issue that when I transfer energy from one location to another, there's a decent amount of energy that gets lost in that transfer process due to heat. If we could transfer our energy along superconducting wires, there'd be no loss of energy due to heat because there's no resistance. In addition, there are some other very, very shocking and surprising properties about superconductors, such as that if I have an object that's a superconductor and I place it above a magnet, it can basically levitate. And this is something that probably in the next class I'll show you guys a video on. You're saying, but wouldn't it take a lot of energy to keep it at 4 Kelvin? Absolutely. Mercury is not a reasonable material to be using as a commercial superconductor, but the fact is that we're finding, more and more we're finding that there are objects that we can get to a superconducting state at a higher temperature. And if you if you could find a type of material that had a superconducting state of at like 150 Kelvin or like close to room temperature or something like that, that'd be really powerful. I know that there are certain alloys, and I'm not going to go into details what they are, but there are certain alloys that have a critical temperature that's on the order of 80 Kelvin. That's a little more achievable. I believe 80 Kelvin is something close to the kind of point at which nitrogen turns into liquid nitrogen. So, I mean, I've personally done a demonstration in not at El Camino, but at a school I worked at before. I did a demo where I supercooled a piece of metal that was a superconductor around this temperature in a laboratory. And then, one of the things that you can do is, like, if you have a magnet. So let's say I have a magnet, and this is the north end of the magnet. And this is the south end of the magnet right here. Let's talk about how this levitation works. This is quite interesting, and I'll show you guys a video next time. But so if I have a magnet set up like this, okay, I'm just gonna ask you guys, what would happen if I took another magnet, okay, and I place it directly above it? I take another magnet that's kind of like a disc like this, let's say, and I place it right here. And I literally place it right on top of it, right here. And let's say I start off and I put my fingers on both sides here, and I hold it in place for a second, right? And then what happens if I let go? You're saying repulsion is. I'm kind of like more interested in what would happen over time. Nathan, you asked. So since there's no energy due to heat loss, wouldn't cooling be easier because you just need to yes. You just need to maintain the temperature and not have to fight the rising temperature in the soup. Yeah, you're right, Nathan. That's right. You just need to be able to make sure that you can maintain that low temperature. You think about it like right now that there's these big efforts to make quantum computers at Google and at Microsoft, right? And these quantum computers are heavily affected by temperature fluctuations, so they have to place them into these rooms that are heavily temperature controlled. You would need something similar to this. Yeah. What would physically happen if I hold this magnet above this magnet? Would the magnet on top just float there? No, it won't. What'll happen? They'll fly away. Depending on how strong they are and how close together I put them, they might fly away. Most of the time, something else would happen, though. You guys all agree it'd probably flip. Exactly, Nathan. That's what happens. They actually flip. They flip until the south end is down and it connects to the other magnet, and they attach to each other. Exactly. They flip and they attach. So I mentioned this just to say that you can't really levitate a magnet on top of another magnet. Now you could, if you really wanted to. You could drill a hole through this magnet here on both sides. You could run a peg through the middle of it. Okay, and now they would kind of float, right? There'd be an equilibrium and they could float on this peg right here, right? But then you're kind of cheating, right? It's not real levitation. Now, and we have like things like that in our lab and stuff like that. Now, what happens if I put a superconductor? Okay. If the peg was free to move, would it stay still? No, it wouldn't stay still. You mean because the flag? I don't know. The peg would flop over if it was free to move, Ash. Like if it wasn't connected at the bottom, the peg would just flop. It wouldn't be able to stay still. Now, if instead I took a superconducting material, okay, and I cool it down to a low enough temperature, what happens is if I take a superconductor, so let's just label it as SC right here. If I take a superconductor and I place it over a magnet, something really strange happens. It doesn't exactly levitate, but it does what you would think is levitation. It basically locks in space. So it literally very much would float right at that location. Now it might spin a little bit, but it would just be chilling, yes. Due to some effects that are related to quantum mechanics, the superconductor gets locked in space, and instead of flipping over like a normal magnet would on top of this, it gets locked in space, and it just floats. It literally just floats directly above this object. It's really amazing to see. It's hard to believe, but what's even stranger, I don't know, I can't rotate in this program, can I? What's even stranger is that if we were to take this object, okay, and if you were to rotate it just a little bit, or I don't know, if you were to, can I tilt these at all? I don't know. It doesn't matter. The point is, if I was to rotate this even a little bit, what's interesting that would happen is, like, let's say that you were to tilt it like a little bit like this. Remarkably, it would just stay in the same position that you place it. It's really strange. And these type of systems can support huge amounts of weight. Yeah, it's kind of weird, Nathan, isn't it? It's kind of weird. So we'll watch a video in class next time about this, about superconductors and about levitation and stuff like that. But all of this stuff is well beyond the physics of 1C. What's happening is a quantum mechanical process that wasn't understood. You said you'd imagine it would move back in equal distance to the magnet. You'd think that if you push it this way, maybe it would like oscillate or something like that. Is that what you're saying? Or like it would flip? Yeah. But it doesn't. It literally just stays there. It locks in space above the magnet. There's a lot of really powerful ways in which this type of technology could be exploited. And they'll kind of be brought up. Yeah, I did this demo at one of my other schools. Yep. It's really simple. We just took a little tiny piece of metal. The metal that we used was some kind of alloy of like a terbium, calcium, it was like a terbium 4 calcium 8 oxygen 12, I don't know, some like, there's a bunch of metals, some kind of alloy that had some calcium oxide, I don't know. And this type of metal just happens to have a really high critical temperature that you can just pour liquid nitrogen over it and you can float it above these magnets. It's utterly amazing. It's utterly shocking. Yeah, it's pretty cool. Superconductors are pretty neat. All right, let's do a real quick problem right here, just to make sure that we understand how to use this equation. It says, suppose the resistance of a copper wire is 1.05. So this is going to be our resistance at 20 degrees Celsius is going to be 1.05 ohms. And the temperature, well, that'll be a T0. That's going to be 20 degrees Celsius. And we want to find the resistance at 0 degrees Celsius and 100 degrees Celsius. And the value of alpha for copper is given right here. Very easy plug and chug problem. We're going to use this equation right here, or realistically this one. Let's block this one in. So the resistance at 0 degrees Celsius would be 1.05 ohms. And then we multiply by 1 plus alpha. And and then times T minus T naught. So then this T is 0 degrees Celsius, the value we want to find here, minus 20 degrees Celsius. That's it. So this would be... I would show you the video tonight, but there just isn't enough time. I think it's like about a 10-minute video, so we run out of time. We'll watch it some point during class tomorrow, or on Tuesday. So the temperature, or the resistance in this case would be 0.9675 ohms. That's the resistance at 0. A little bit less. A little bit less. Man, sitting in my chair like this, my back starts to hurt a lot. Okay. Well, I mean, we might as well just watch it during class when we can, like, really sit around and talk about it, though. Yeah, you can go watch it. It's just, go look for Superconductors on Google. I'll show you which video it is. This is a TED Talk. Superman pose. Close. This is an old TED Talk, but it's still really good. It's 10 minutes long. I'll tell you what, we'll skip to the good part. Skip to the good part, that's what we'll do. He shows it at the beginning, actually. Where's the... There we go, sorry. See, there it is. It kind of falls down.
The phenomena you saw here only below a certain...
Here we go. We're gonna go straight to the good part. We'll watch the whole video next time.
And sometimes it's not just superconductor will be... So we got one conductor that is a circular rail here.
So he's got a circular magnetic rail.
And an arc magnet and make whatever track I want. For example, I can make a large circular rail here. And
oh, you guys can't hear the video, can you?
I place the superconducting disc.
That's okay. We'll deal with that
on
next
top
time.
of this rail. It moves freely.
Oh, because it's playing through my TV, right? Yeah. There you go.
And
So
again,
just imagine,
that's
you
not
know,
all.
it could be a hoverboard, and you could be standing on it. You could be going around in circles just like that. It can hold a huge amount of weight because it's related to something called quantum locking. And there you go. Yep. So if you want to go find that, not hard to find, Levitating Superconductor. It's from 2012, so that's almost 8 years ago, which is crazy. But definitely very interesting, and we'll probably watch that video and talk about it. It might be something that would make more sense to talk about, like, once once we actually talk about magnetism first. But since it's not really related to magnetism, it's actually related to something called quantum locking. Maybe it's okay. All right, I'm going to stop the recording there. If you guys have other questions, feel free to sit around and ask.